A model for the motion of a spring. Let's now look at an example of a model from the physical sciences. We consider the motion of an object with mass m at the end of a vertical spring, as in figure 4. In section 6.4, we discuss Hooke's law, which says that if the spring is stretched or compressed x units from its natural length, then it exerts a force that is proportional to x. Restoring force equals negative kx, where k is a positive constant called the spring constant. If we ignore any external resisting forces due to air resistance or friction, then by Newton's second law, force equals mass times acceleration, we have equation 3, m times the second derivative of x with respect to t squared equals negative kx. See figure 4. Equilibrium position and graph going downwards, x along the vertical axis to another m. Returning to the text. This is an example of what is called a second order differential equation because it involves second derivatives. Let's see what we can guess about the form of the solution directly from the equation. We can rewrite equation 3 in the form the second derivative of x with respect to t squared equals negative k over m times x, which says that the second derivative of x is proportional to x, but has the opposite sign. We know two fractions with this property. The sine and cosine functions. In fact, it turns out that all solutions of equation 3 can be written as combinations of certain sine and cosine functions. See exercise 4. This is not surprising. We expect the spring to oscillate about its equilibrium position, and so it is natural to think that trigonometric functions are involved. General differential equations. In general, a differential equation is an equation that contains an unknown function and one or more of its derivatives. The order of a differential equation is the order of the highest derivative that occurs in the equation. Thus equations 1 and 2 are first order equations, and equation 3 is a second order equation. In all three of those equations, the independent variable is called t and it represents time, but in general, the independent variable doesn't have to represent time. For example, when we consider the differential equation, equation 4, y prime equals x times y, it is understood that y is an unknown function of x. A function f is called a solution of differential called a solution of a differential equation if the equation is satisfied when y equals f of x and its derivatives are substituted into the equation. Thus, f is a solution of equation 4 if f prime of x equals x times f of x for all values of x in some interval. When we are asked to solve a differential equation, we are expected to find all possible solutions of the equation. We have already solved some particularly simple differential equations, namely those of the form y prime equals f of x. For instance, we know that the general solution of the differential equation y prime equals x cubed is given by y equals x to the fourth power over 4 plus c, where big C is an arbitrary constant. But in general, solving a differential equation is not an easy matter. There is no systematic technique that enables us to solve all differential equations. In section 9.2, however, we will see how to draw rough graphs of solutions even when we have no explicit formula. We will also learn how to find numerical approximations to solutions. Example 1. Show that every member of the family of functions y equals 1 plus c times e to the power t over 1 minus c times e to the power t is a solution of the differential equation y prime equals 1/2 open y squared minus 1 close. Solution. We use the quotient rule to differentiate the expression for y. Y prime equals open 1 minus c times e to the power t close open c times e to the power t close minus open 1 plus c times e to the power t close open minus c e to the power t close over open 1 minus c to the times e to the power t close squared equals c times e to the power t minus c squared times e to the power 2t plus c times e to the power t plus c squared times e to the power 2t over open 1 minus c times e to the power t close squared equals 2c times e to the power t over open 1 minus c times e to the power t close squared. Sidebar, figure 5 shows graphs of 7 members of the family in example 1. The differential equation shows that if y is approximately equal to plus or minus 1, then y prime equals 0. That is borne out by the flatness of the graphs near y equals 1 and y equals negative 1. Figure 5, see figure 5. Back to the text. The right side of the differential equation becomes 1/2 open y squared minus 1 close equals 1/2 open bracket open 1 plus e times e to the power t over 1 minus c times e to the power t close squared minus 1 close bracket equals 1/2 open bracket open 1 plus c times e to the power t close squared minus open 1 minus c times e to the power t close squared over open 1 minus c times e to the power t close squared close bracket equals 1/2 times 4 c e to the power t over open 1 minus c e to the power t close squared equals 2 c e to the power t over open 1 minus c e to the power t close squared. Therefore, for every value of c, the given function is a solution of the differential equation. When applying differential equations, we are usually not as interested in finding a family of solutions, the general solution, as we are in finding a solution that satisfies some additional requirement. In many physical problems, we need to find the particular solution that satisfies a condition of the form y open t sub naught close equals y sub naught. This is called an initial condition, and the problem of finding a solution of the differential equation that satisfies the initial condition is called an initial value problem. Geometrically, when we impose an additional condition, we look at the family of solutions, solution curves, and pick the one that passes through the point open t sub naught and y sub naught close. Physically, this corresponds to measuring the state of a system at time t sub naught and using the solution of the initial value problem to predict the future behavior of the system. Example 2. Find a solution of the differential equation y prime equals 1/2 open y squared minus 1 closed that satisfies the initial condition y open 0 closed equals 2. Solution. Substituting the values t equals 0 and y equals 2 into the formula y equals 1 plus c e to the power t over 1 minus c e to the power t. From example 1, we get 2 equals 1 plus c e to the power 0 over 1 minus c e to the power 0 equals 1 plus c over 1 minus c. Solving this equation for c, we get 2 minus 2c equals 1 plus c, which gives c equals 1/3. So the solution of the initial value problem is y equals 1 plus 1/3 e to the power t over 1 minus 1/3 e to the power t equals 3 plus e to the power t over 3 minus e to the power t.